Hello, everyone. Thank you for joining this session today. So I will be walking you through our Iceberg migration and the cost savings that we have achieved along. So let me start with introducing myself. So I'm Dennis. I've been working at Insider for the last 6 years, and I'm mainly focused on the machine learning and big data solutions on AWS. And in today's agenda, we will see an end-to-end view of our migration from Hive to Iceberg. And I'll start with data lake usage at Insider and why we have decided to migrate from Apache Hive and why we have selected Apache Iceberg. Then I will talk about how we designed and executed the migration and what was the outcomes. So let's start with our data lake. So Insider is a SaaS marketing platform, and we've been integrating with customers all around the world, and we have more than 1,000 clients of us, and we are collecting, like they are mostly e-commerce companies, let's say, and we are collecting their end users' data, like the clickstream activities on their website, mobile applications, their CRM data, and the activities in the messaging channels like web push, SMS, WhatsApp, and so on. And we are using this data to improve their user experiences and provide marketing automations. So we ingest this data into our data lake in JSON format, and we are running streaming, hourly, and daily ETLs to clean, improve, and insert this data into our structured data sets. So some of our pipelines use this structured data in our data lake directly. And specifically, our machine learning pipeline requires machine learning ready features, which are extracted with several feature extraction jobs from our structured data and applied, like we are applying operations like aggregations or extracting embeddings and writing them back to our data lake for the downstream machine learning operations like training and inference. So overall, we are running more than 15,000 Spark jobs every day to fill our creative customer segmentation, product recommendations, channel engagement prediction, and reporting, and so on. And most of these jobs are actually running in our machine learning pipelines, which are running for more than 10 products internally and consists of the feature extraction, selection, model training, evaluation, and inference tasks. So we were using Apache Hive till our migration for like 6 or 7 years. But throughout the years, with us scaling out, we saw several issues with Apache Hive. So let's start with the correctness one. As Hive has no SS support, we've seen some correctness issues. Like as the write operations are not atomic, you can be at bad state if you have an incomplete write. Like if you have written some data files but failed to write some, Apache Hive is perfect, completely okay with this. And it leaves your data set in a bad state. From the point of isolation, if you have parallel writes to same dataset and same partition, you may have race conditions. Or if you are reading that partition, like if you, during your read operation, if there are some other write operations or delete operations, you don't have a consistent view of the dataset. So these are the correctness issues that we have seen. And also, on the other side, there is the performance issues. So our query engine is Apache Spark, and for Spark to execute a query, first it needs to plan the query. So during the query planning, first it needs to find out which partitions of the table that is required to be read, and to do that, when using Hive, we are querying Hive Metastore, which is a MySQL table, MySQL database. So we are querying the Hive Metastore to find out which partitions match with the query we have provided. So after finding out the partitions, we also need to find out the actual data files, because, for example, we are using Amazon S3, or like for any object storage or file storage, you need to know which data files to be read. For example, for the S3, you need to execute S3 get API calls for each and every object key to read the data set. So you need to know which keys exist. And in order to do that, in Hive, the data files within the partitions are discovered using directory listing. And in an object storage like S3, a directory listing is basically searching for objects with the same prefix. So it's a costly operation, and if you have n partitions, it's an O(n) time complexity operation, which is costly. And finally, when we look at the cost side of our, like when we look from the cost perspective to our data lake, we have found several possible optimization points. The first of all, as we just talked, the S3 list bucket calls for directory listing to Hive was expensive. And then there is the S3 head object and get object calls to read each and every data files. And if you have small files problem, there are a lot of files to read, and this is expensive. Of course, this is not directly related with Hive, but in our data lake, we had this problem for several tables we wanted to solve. Then we thought that we can even decrease the storage size with using like the more recent compression techniques. We were using Snappy at that time. Then there is the wasted compute resources, like the EC2 instances and our EMR clusters. We're just waiting for Spark query planning to be finished. And last but not least, we were running an RDS instance, a MySQL instance, solely for Hive Metastore, and we wanted to get rid of that. So those were the points that pushed us to a migration, to find a better solution and a migration. So why we have selected Apache Iceberg? So if you are talking about the lakehouse architectures, here is your usual suspects: Apache Iceberg, Apache Hudi, and Delta. So basically, they are similar. Like all of them have asset transactions, which is crucial. They have time travel feature, which is really nice for rollback scenarios. You can use Parquet data file and so on. So there are several different like distinguishing features for each and every option. And for Delta, at the time we were evaluating, the performance features were not included in the open source version. And as we were using Amazon EMR for whole Spark clusters, that was a big no for us. But this have changed recently. But at that time, it was a like red flag for us, so we just eliminated it. Then we left with the Iceberg and Hudi. For Hudi, actually we like the primary keys and the duplication features. On the Iceberg side, we like the partition evolution and hidden partitioning features. And as we had like previous problems with like changing the partition schema of a table, like we wanted to change the partition. We had a full migration for that table in Hive. It was a big operation and so on. We really like the partition evolution and also hidden partitioning features. So we selected Iceberg for that. So let's see how Iceberg solves our issues. And let's start with the correctness issues first. So as Iceberg supports asset transactions, actually the correctness issues are solved out of the box. Like the atomicity issue that we talked about is solved as the write operations are atomic, and the metadata is updated when the data files are fully inserted. So if you have an incomplete write in Iceberg, basically the metadata file is not updated, and the data files you just have written are not a part of the dataset. For the isolation, if you have parallel writes, it is supported by optimistic concurrency. And you can even do better if you are using the REST catalog. From the reader point of view, since Iceberg uses metadata and snapshot to read a dataset, while you are reading the dataset, you go through the snapshot in metadata, so you know which data files are in that snapshot. So even if someone else, some other producer writes in new data, or even if the data files are deleted by a commit, your read operation is not affected, and we have a consistent view of the dataset. On the other hand, from the performance side, so during the Spark query planning, now we are using metadata to both find out the partitions and the data files. So the high meta stored bottleneck is removed, and using the metadata, now the file pruning and predicate pushdown operations are a part of a distributed planning. And also to find out the data files, we are using metadata file, which has the list of data files. So via a single RPC call, we can find out which data files to read. So it is now a one-time complexity operation for n many partitions. So it's a huge step forward if you have a lot of partitions, especially. So finally, before the migration, we had to select the new data file and compression algorithm to move forward. So we have done several benchmarks, and we selected Parquet file format with ZSTD compression algorithm. And we have found out that when you order the string columns, like the sort the string columns, you can even get better compression rates. So here we see a sample data file, which has around 550 megabytes when it's uncompressed, and it can be compressed till 177 megabytes, which is around 70% compression when we are using ZSTD and order the string columns. Of course, this can change with respect to your data file, like the data you are storing and cardinality of the string columns, but it was a better option than Snappy, and ordering the string columns were, of course, definitely beneficial. So that was all the work before migration. Let's continue with the what was our requirements, planning, and execution of the migration. So let's start with the requirements. At the time of the migration, the state of our data lake looked like this. So we had 15 tables, around 500,000 partitions, and more than 100 terabytes of data files. Then we want to change our file type from ORC to Parquet, and we also wanted to use the ZSTD algorithm for compression instead of Snappy. And finally, we also wanted to have table-level modifications, like changing the partition, schema, and even data for several tables, sorry. And when we look at it, it was pretty easy to see that it was not possible for us to have an in-place migration, and we had to perform a full migration. So we planned the full migration without downtime. And it was like that. So first, migrate all the available data to Iceberg. And then, like in parallel, start writing new data into both Hive and Iceberg and have the datasets synced. When the datasets are synced, start reading data from Iceberg. So after all the readers are updated to use Iceberg, have some time to monitor the system. And when everything is all right, stop writing in Hive and delete all data in Hive, also terminate all the resources. That was the plan. And to execute the plan, we built a temporary pipeline for the migration. And we have used Spark for heavy lifting and Redis for storing the migration metadata. And finally, we have used Grafana to monitor the migration process itself. And the Spark job was responsible of reading data from Hive table, then transforming that if it's required for that table. For example, we might have changed the schema, or we might want to apply some transformations at data level, then write that into Iceberg table. And each Spark job takes a table name as a parameter. So one Spark job run, a single Spark job runs for a single table in its lifetime, and it finds out which partitions to be migrated from a Redis instance. So in a Redis instance, we store the partitions of Hive tables in a Redis set. So we knew that which partitions are not migrated yet. So the Spark job, having the table name, goes to Redis, reads the Redis set, and until the set is empty, it pops migration partition metadata, and using that partition metadata, reads the Hive table and writes into Iceberg table, and continues like that. This approach enabled us to scale the migration process by simply adding new Spark jobs. And to decide on that, we were using our monitoring dashboard in Grafana. So we were writing the progress in Spark job to the Redis instance, and we were also logging that in Spark driver logs. So on the right-hand side, you can see a screenshot from our staging. It shows like the progress and number of partitions. We wrote this in Redis instance, and using the Redis plugin in Grafana, I just showed it to our internal users. So we knew the progress for each table, like how much percentage of it is completed, how many partitions we have left to migrate, and what is the estimated time. So if we think the estimated time to finish the migration for a table is longer than required, we can simply add new Spark jobs and add new resource to just decrease the time by parallelizing and accelerating the migration. So this helped us to see the progress of the migration. And finally, let's see what was the outcomes of our migration from cost saving and performance perspectives. So half of our savings were from S3 side. So the S3 cost for the bucket that we were using for our data lake went down by 90%. And the main driver for this was solving the small files issue. Of course, there are other ways to solve this issue, like using the Spark partition, number of partitions, etc. But as a SaaS product, we had same data set with several megabytes for some clients and tens of gigabytes for some other clients. So using the number of partitions wasn't the optimal solution. And Iceberg just solved it out of the box. So it was a pretty easy fix. And how Iceberg does it is out of the box, Iceberg just writes out data files in 512 megabytes. And this is configurable for each table by the write.target file size bytes configuration here. So by just updating the table properties for this configuration, you can change the table file, the data file bytes for that particular table. So also, if you're interested in the managing data files in Iceberg, there is another session tomorrow from Russell Spitzer by Russell Spitzer from Apple called Managing Data Files in Apache Iceberg. So I also encourage you to join that session as well if you are interested more in that topic. So this feature enabled us to reduce the object count by 94% in S3. And also our storage, the number of bytes, and therefore the cost reduced by 35% using ZSTD. And since we were having bigger files, also the compression worked better. Like the bigger file, the better works the compression. Therefore, the small file, solving the small file problem also helped the reducing the storage amount as well. So that was from the S3 side. And the other half of the savings were from compute size. So basically our EC2 instance and EMR clusters, cost for them went by 24%. And this was this is achieved by removing the bottlenecks of Hive meta store, like querying the Hive meta store and having the ON directory listing on S3. Removing these bottlenecks accelerated the query planning a lot. And also, again, having the fewer and bigger data files having better I/O performance. So our Spark jobs enjoyed around 24-25% acceleration, which directly, of course, reduces the bill for EMR and EC2. And when we combine our savings for storage and compute, we ended up with 5-digit US dollars per month, which was amazing. And I think that was the biggest ROIs that we have seen from a migration at Insider ever. And that was it from my side. So thank you for joining this session and listening to me till the end.